So that's an important announcement. Change for this semester. In addition to the simple project, you'll also have an extremely simple exam, perhaps in the form of multiple choice questions. I've just started recording here again, yeah? So with that announcement out of the way, let's save it. So I can put this picture on Moodle as well, perhaps, yeah? Let's go into today's topics. Perhaps you know I already had this 2-hour class between 10 o'clock and 12 o'clock, so I have some drawings over here and things, but okay, let me start from the start and draw all of that again, because it's easier for you guys to understand what we're talking about. And we're going to start with encryption. Whenever I have some typos, excuse me for that. Now, because now you are going to have exams, right? Perhaps it's a good idea to take note of whatever I'm talking about. Yes, all of these are kind of explanations of things. Those will be on the exam. As you see over here, I've saved these explanations in a PPT, and I've already uploaded this to Moodle, and there will also be a video of everything that I'm going to talk about now. So even if you don't take notes, it's still kind of okay, but then you'll have to watch the video a few times to understand everything, right? Or you can just take notes, right? So we're going to start with encryption, okay? So encryption is nothing new, even though this is a smart tech course. Encryption is nothing new. We have used encryption. People have used encryption for over 1,000 years, right? Basically, encryption is some kind of way of hiding the information. So if I just go to Google and search for encryption, go to images, let's actually do that. You see encryption, and maybe simple encryption, something like that. I go to images, I see a lot of examples over here. Let's look at this one, right? Here's an example of extremely simple encryption. Let's say every letter in the English alphabet will be turned into a number. For example, A is 1, B is 2, C is 3, D is 4, and so on, right? Then I'm going to encrypt the message with some kind of way. We'll call this a key, right? Like a key. For example, my key can be number 3. I just take the number of each letter, add 3. And that will be the way to encrypt or to hide the information. So for example, if I'm a spy and you are a spy, we are both spies among the enemy, right? We need to exchange some information. We don't want the enemy to find out what is information, right? I want to write down hello to you. I cannot write down hello because then the enemy find out that I say hello. So what I do is simple encryption. For example, in this case, I just add 3 to every letter. A, B, C, D, E, H, I, J, K, right? 3 letters after H is actually K. 3 letters after E is actually H, and so on. So this is an example of encryption, but this is too simple. This is the type of encryption this is the type of encryption people used more than 1,000 years ago, right? This is too easy. Nowadays, of course, we don't really use it, but this is just an explanation of what is encryption for you, okay? Right? So this is an example of symmetric encryption, where the same key is used for encrypting and decrypting. In this example, the key is 3. So let me take a picture of this so we can put it on Moodle as well. So I know what is this example. So you know what this example means when you are looking at it in Moodle, something like this. Make it a bit smaller, right? There it is. So in this example, once my friend, another spy, gets the message KHOOR, he will have to use the same number 3 to get back to the original message. So decrypting is getting back to the original message, right? and I have typos here, opposite. So if I do have some typos that I don't catch in the future, excuse me for that. Opposite of encryption. Find the original message from the hidden info, right? Something like that, right? Okay, so this is an example of symmetric encryption. It's pretty simple nowadays, especially for blockchain and Bitcoin and many other blockchains, right? We use asymmetric encryption. Where a different key is used to encrypt versus and decrypt information. Okay, so asymmetric encryption uses a key pair. It's the asymmetric encryption that uses the key pair. Okay, there are two pairs, or two keys. They are called private key and public key. Private key and public key. Let's save this. Save. This is what I was explaining last hour. I think it looks better this time. So let's save it on top of number 1. Yes, replace it. Okay, public key and private key. Okay, now how does the asymmetric encryption work? Now let's create a new file, part2 let's say, and replace it. Now let's just delete everything. So private key is the only key, so let me rewrite this. Public key is the only key that can decrypt the information that was encrypted using the public key, and vice versa. Let me write it down and then I will explain this. So if you don't really understand, that's fine. I'm going to explain it. Public key is the only key that can decrypt info encrypted by private key. So here's how it works. Let's say, for example, we are in the enemy territory. I'm a spy, you're a spy, right? We're trying to help our country, but we're among the enemies. Okay, so we want to exchange information. And this message, maybe the enemy can catch the message, right? So I want to encrypt the message so they don't know what I'm saying, okay? So if I encrypt the message using my key, just like we did over here, so that's basically just mix up the information using a number, right? But instead of number 3, the key is going to be very difficult, very hard, very long, right? So I'm going to use a public key to encrypt it. But the mathematical function is now different, not just simply rearranging the letters in the alphabet, right? So the only key that mathematically can decrypt information is the public key that you have. Okay, so I take some information and I encrypt it, then send it to you. Even if the enemy gets the information, let's say they don't have the public key, right? Then they can't decrypt it, okay? If you receive it, you can decrypt it, okay? And because your key can only decrypt the information that was encrypted by my key, you know that it's coming from me, not coming from the enemy trying to give you misinformation. You understand? Okay, because private key and public key come in a key pair. They only work with each other, no other keys, right? One key can decrypt what the other key encrypts, and vice versa, okay? Or vice versa. Let's say you are back let's say all of you are back in the home country, and I'm the spy. We're all in the military. We try to help each other, right? But we can't communicate. You're at home country. I'm among the enemies, right? You want to give me some information. She wants to give me some useful information, and he wants to give me some useful information. But we can't call each other, right? So you can encrypt something using my public key, okay? And maybe just put it in the newspaper, whatever, right? It doesn't matter, because even if the enemies get this information, only the holder of the private key can decrypt it, right? So you will know that the enemy will not get that information. Only I will get it, because hopefully I'm the only one who still has that public key. Perhaps they didn't torture me to get that public key out of me, or private key out of me, right? Okay, so that's how a pair of public-private keys work, okay? So that's really, really cool. That's also connected to digital signatures. We're going to talk about digital signatures at the end of hour number 2, okay? So that is, so far we covered the topic of encryption, okay? And a key pair, okay? So that's saved as the second one, okay? So next what we're going to do is we're going to apply this to a blockchain, okay? How all of this is actually used in a blockchain. Specifically Bitcoin, but there are many other blockchains as well, right? So before we move on to how it's all used in the blockchain, first let me answer the question, why, right? People participate in the Bitcoin blockchain. Why do they download over 300 gigabytes of data and keep track of all future Bitcoin transactions? Why would people do that, right? Well, the reason for that is because, well, actually, this process is called mining. Well, which process? The process of keeping track of all transactions. Maybe you guys have heard about Bitcoin mining. Maybe yes, maybe not. We're gonna have a look at a very interesting brief video, so that'll be pretty cool. But that is called mining, right? And why do people participate in mining? Because they get a reward. Okay, so the answer to this question is that BTC miners, they're called miners who are participating in the mining, right? They are rewarded with new Bitcoin. New Bitcoins are created in every block, and every block, on average, sometimes it takes longer, sometimes it takes shorter, but on average, every block appears every 10 minutes. Okay? Let's move it up a little so it looks a little better. Okay? So save it as picture number 2, and let's have a look at Bitcoin mining. Did I show the mining in the previous example, in the previous hour? Yes, I did. So here's an example of a mining farm, right? That's basically how people do that.
Running all the cables in the right way and putting all the components together is not very difficult. The difficulty...
We don't need to listen to what they're talking about. We're not going to even watch for 4 minutes, just a few seconds, just to give you an example.
The difficulty is how to handle the logistics and the preparation for building a farm of this scale.
This Iceland.
Hi, I'm Philip Salter. I'm handling... You wait for it.
Basically, as you see, there are hundreds and hundreds and hundreds of computers in every mining farm, right? And there are many mining farms all over the world. There are many in China because electricity is cheap in China, right? There are many in Iceland, many in Canada because you don't need to spend time on air conditioning the room in those countries because it's already cold. Why do you need to spend electricity air conditioning the room? Because when the computers are working, all the electricity is moving all through the components. They're heating up, and computers are heating up. And usually computers work much better, much faster when they're cold rather than when they're hot. Okay, so that's why mining is really popular, especially in northern countries and wherever electricity is cheap, such as mainland China, for example. Okay, So this is just gives you an example that thousands and thousands and thousands of computers are actually involved in Bitcoin mining. Why so many are involved? Anyone can actually do that. All you need is to download 300 gigabytes of data of all of the transactions that happened since 2009, right? And just keep track of all the new transactions. It's not going to be that hard. I can just do it up in my office over there. You just need one computer for that, right? The thing is, not every miner is actually rewarded with newly created Bitcoins. If I download the whole blockchain, I actually did on my very old laptop. It's very simple, just 300 gigabytes of data is nothing. I did the mining, but I didn't win any Bitcoins. Why? Because the new Bitcoins every 10 minutes are not given to all of the miners. New Bitcoins every 10 minutes are given to one miner. Every 10 minutes are given to one miner who is the fastest, who is the first to solve a mathematical puzzle. We're going to talk about those mathematical puzzles. That is why people dedicate so much computing power into their mining farms. Where was it? Here. Because they want to win this race. Every 10 minutes there is a race within a new block for new Bitcoins. Okay? We don't know who will be the first to solve that mathematical puzzle. So if your computers are faster, if you connect more computers all together, then their combined brain is faster, right? Then perhaps next 10 minutes it will be you who will get the new Bitcoins. Well, if not next 10 minutes, then maybe the next 10 minutes after that. Or, well, if not, then maybe the next 10 minutes after that and that, right? So that is why so much computing power is actually dedicated to Bitcoin mining and also mining of other cryptocurrencies as well, okay? So that is the reason why. And you don't have to dedicate so much computing power to mining. You can, for example, have an additional copy of that blockchain, just like we had a hands-on approach last week, right, where we had the paper copy of the blockchain, right? You could do that with your computer, but the thing is, perhaps never in 100 years you will win the race for new Bitcoins, right? Because you, using some old computer, are competing against hundreds and hundreds of mining farms, each with thousands of computers, right? So I have never won a new reward in a blockchain, although I have maintained the blockchain for a while in my office upstairs, right? So the rewards are actually pretty cool. So if you look at, what did we look at over here? Yeah, that was the last picture we made before we finished the previous class. Rewards in Bitcoin actually decrease. They halve every 4 years, okay? So every 4 years, this reward that comes every 10 minutes in Bitcoin is decreased by half. So since 2009, as you know, Bitcoin was created in 2009, right? Until 2012, right? Every 10 minutes, 50 new Bitcoins were given to one miner who was first to solve the puzzle. We're going to talk about the puzzles soon, okay? The mathematical puzzle, right? After that, it's half, 25 new Bitcoins were given to one miner every 10 minutes who was the first to solve a puzzle, then 12 and a half. Then in May last year was the previous halving, that's called halving. Now the reward, still until now, is 6.25 of Bitcoins is given every 10 minutes to a miner who wins this race, right? Next halving will be 2024, then 2028, 2032, and so on, right? So that is the reward, pretty substantial, right? That's every 10 minutes, and the Bitcoin price right now is around $50,000 US, right? So 6.25 times $50,000 US, I'm not really sure how much it is, probably around $300,000 or so. You perhaps might buy a house for that, right? But I mean, you are competing against a dozen and dozen of other mining farms, each with thousands and thousands of computers, right? So the original investment is also pretty substantial, right? So that's the answer to the question why people do that and why this is a big industry. That's why we are studying about it, okay? Let me see what was the third picture, and okay, that's why, mining rewards, let's just, okay, now we move on finally to the blocks and things, what is happening over here. Okay, right. So, as we said, let me check if I'm still recording. Looks like I am still recording, and this thing is jumping left and right into the yellow and red, so the audio is recording as well. So as I said, the miners are competing to solve some kind of mathematical function, right? So let's talk about those functions. Okay, there are two functions that we need to learn. One of them is encrypting, decrypting. We've already kind of looked at that. Another one is hashing. So let me open Paint again, and let me connect with what we've been talking about, right? So miners race to solve some puzzles, right? The puzzles are the mathematical one-way function. One-way functions in mathematics are also called trapdoor function. Imagine if I put a trapdoor in that floor. If you walk over that trapdoor, you'll drop down, right? So you just go one way and you cannot climb out because it's too deep. That's called a trapdoor, right? So let's see what Google gives us for trapdoor function, okay? So that it's kind of easy to understand maybe. So here's an example of a trapdoor function. You see, it's easy to go from here, from right to the left. You see, it's easy to go this way, but to go back is very hard. So that's in mathematics called a one-way function. Another word for that is trapdoor function. Well, let me give you some more pictures if this is not very illustrative. Let's go back to Google and trapdoor function math images. This is the same image, right? That's an actual example. There are many different kinds of trapdoor functions. There are ellipticals used in trapdoor functions. This is the elliptic curve cryptography used in actual Bitcoin blockchain. Hard to find an illustrative example because the actual calculations are quite complex. We don't do them by hand. Okay, so hard to find another picture. Maybe I'll just use this picture because it has color. So one more picture here, and maybe I can write down something like easy to calculate D from R, but cannot calculate R from D. Okay, that is a trapdoor function, right? So for example, if I give you x plus 5 equals 3, this is a not trapdoor function, right? Because you can calculate both ways, right? So for example, if I give you x plus 5 equals y, this is not an example of a trapdoor function, right? Because if I give you x, you can calculate y. If I give you y, you can calculate x, yes? Can you? Anybody not? Right? It's too easy, it's not a trapdoor function. Actual mathematical trapdoor function formulas are really difficult. Okay, so I'm gonna save it. How are we gonna save it? That's already probably picture number 3. Okay, so there are many different kinds of Control delete, and this will be picture number 4. Okay, so there are many different kinds of trapdoor functions or one-way functions in mathematics. The particular kind that is used in blockchain is hash function. And finding the output, the result of the calculations is called hashing, right? And the hash function, okay? And also, there are many different types of hash functions. One that is used in Bitcoin the name of this hash function, that are different, right, is called SHA-256, because the result, the output, is always 256 bits long. right? Bits in computer science is zeros and ones, right? Because everything inside a computer is just zeros and ones, right? Okay. So let's have a look at SHA-256. By hand, we can do these calculations by hand, but it's extremely difficult. So if we go to YouTube, we can actually find some SHA-256 calculations by hand. You see, these are the calculations you have to do. It takes 8 minutes to just calculate one step, and there are 2,000 steps as far as I know in SHA-256. So it's really, really difficult. Computers do that really fast. Of course, by hand, you'll take like ages to do just one calculation. So here's an example of SHA-256. You will have to do this. This will be one of the questions on the exam. I don't have much to ask about calculations, so I'll probably ask, oh, calculate the result of SHA-256 hashing for your name or something. Okay, so just go to Google. Okay, here's what I did. Just go to Google and say SHA-256 online. That's all. Very easy peasy, nothing schmeezy. Just go here. Here it is. Okay, we'll put anything here. For example, my name. This is the output of scrambling my name into this hash. This is called hash. Okay. So hashing is just scrambling the data. Okay. Let's move this down. Perhaps you are taking notes. Perhaps you'll have to watch the video a few times. Scrambling the data is different from encryption. Because with encryption you also have decryption, right? You can go there and back. But with mathematical one-way functions you cannot go back, only there. You understand? So imagine this is x and this is y, yes? So if you put x you can get y, but if you have y you don't know how to get x, right? So for example, imagine you don't see what I'm putting here. This, for example, you didn't see what's here. Imagine you don't see what's here, right? So this is y. Control C, I give you this y, right? I put it on Moodle. Control V, this, I give you this output, this hash, and I ask you, can you please find out what was the x to find this y? You will never be able to do that because mathematically it's a one-way function. You understand? So that is the difference between hashing and encrypting. Hashing is just one-way function. Goes one way. It's just scrambling the data, that's all. But encryption, decryption is scrambling and unscrambling, being able to unscramble as well, okay? And another thing that you can notice over here is, even if I put something very small here, just 11, the output is very long, right? Or if I put something very long over here, the output is still the same size. That's why it's called SHA-256, because the output is always 256 bits long, right? So there are several features of hashing, and that will be on the exam, right? The output is always the same length, right? Maybe 256 or different ones, because there are different types of hash functions, right? Regardless of the input. If you just put my name here, Gooch, the output is 256 bits long. Or if you put a lot of things there, the output is still 256 bits long. That's a special way of just scrambling the data. Cannot unscramble back. Okay. Another thing, let's check another thing. What if I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 here? Okay. Here is the output, right? Now, no, let me use another example because I don't know what is that number. It's too long for me to guess. So let me say 1 million. Here, 1 million, right? This is 1 million. Okay, here's the output, right? Now let me change this just a little bit. Instead of 1 million, I'll have 1,000,001. Let's see how much the output will change. Oh my God. You see it changes a lot, right? So even if you change the data a slight bit, this whole thing changes so much. Oh my God. So that's the second feature of hashing, okay? Slight changes to input, change the hash output. I don't have to say output because hash is the output, okay? Or not really completely. It doesn't have to, maybe just by chance it doesn't change completely, but substantially. Did I spell it correctly? I don't know, it doesn't matter. You will fix my language a bit later, right? And another thing is, let's put 1 million here. 1, 2, 3, 4, 5, 6. What's the output? 6 CCE E45, right? Okay, let me delete that and try 1 million. Try something else. So it's all scrambled. And again, 1 million. 1, 2, 3, 4, 5, 6. 6 CCE E45. Okay, so the scrambling is not random. It's not different every time. It's one particular one-way mathematical function. So the third feature is that hash is same for the same input. Okay? It's not random scrambling. Okay? Whew. Those are hash functions. And as you know, there are many types of hash functions, particularly in Bitcoin. SHA-256 is used, it's this one, right? Now, how it's used in blockchain. Let's move on to, where was I? I'm here. Let me F5 because I already broke something here. What is a block? From last week, a block is just a list of transactions, right? And remember, I showed you a blockchain last week. Let's have a look at an example again. I already don't have it. Let me open it again. So that's blockchain.com. If we look at an explorer, let's go to explorer over here. And these are the latest blocks, right? So let's go to the latest one, 704,622 blocks. And these are the list of transactions. This guy is sending to this guy and this guy these amounts, right? So as you see, there are no names over here. You already know this from last week, so it's just a bit of a review, but this just helps you to understand what's happening over here. There are no names in the blocks, right? There are only addresses, right? So block is simply a list of transactions, right? So block is just simply some kind of information. Where did I over here, right? So instead of hashing my name, or instead of hashing 1,000,001, I could just hash another kind of information. So for example, block number 704,622, right? So for example, 4 bitcoins from Gooch to Jenny, right? 3 bitcoins from Sally to Mavis, something like this also can be hashed, right? And here's the output. So basically how it's applied to blockchain is just think about a block as a piece of information as well, right? And all of that information can also be hashed. Okay, so here's actual hands-on example. Here's an example of a blockchain. Remember, a blockchain is just a connection of blocks. This is block number 1, block number 2, block number 3, and so on. Block number 5 is just a list of transactions, right? This guy, from this guy to this guy, $7. In this case, not bitcoins, dollars, doesn't matter, right? From this guy to this guy, let's say 6 bitcoins. From this guy to this guy, 4 bitcoins. From this guy to this guy, 9.95 bitcoins, right? Okay, so it's just a list of transactions. We also see signatures here. As I said, we're going to talk about digital signatures near the end of hour number 2. Near the end of next hour, we're going to talk about that. But basically, it's just a list of transactions, as you see. And if you take all of this information and hash it, this will be the output. This will be the hash of all of the block. And the block also has previous block hash. It shows the previous block had this hash. Oh, let's check. Let's go to the previous block. Oh yeah, 0000F79349. 0000F79349. Oh yes, absolutely right. This and this, they're the same. So that's how the blocks are connected. Okay, that's how the blocks are connected in the blockchain, and I'll explain why it's important the way they are connected after the break. Any questions right now?